Well, and hopefully you're doing well. In this video, we're going to take a look on chapter 4, probability. I don't know if you ever had a chance to talk about statistics with your friends, with your colleagues, because, the main objective of this chapter for us is to develop a sound understanding of probability values and then use those values to identify when results are significant, right? So that's very important. We're going to do that because probability values constitute the underlying foundation on which methods of inferentials are built. So it's very important to learn how to identify probabilities as values between 0 and 1. Remember, those are all decimal values or fractions. Proper fractions between 0 and 1 decimal, and interpret those values as expression of likelihood events. So we're going to have a chance to develop the ability to calculate probability of events, understand and apply the rare event rule for inferential statistics to determine when results are significant. So define the complement of events and calculate the probability of that complement. So that's what we're going to do in the first section of this book, because as we said, we're gonna take a long time to talk about this because probability is very, very, very important. We're gonna learn how to determine the probability of an event. Okay, so very important to understand the importance of conditional probability, so that we're gonna talk about it in this chapter. So as we said, section 4.1, basic concept of probabilities. The single most important objective of this section is to learn how to interpret probability values, which are expressed as values between 0 and 1. A small probability such as 0.001 or 1 over 1000 corresponds to an event that rarely occurs. Next, also, we're going to talk about odds and how they relate to probabilities. Odds are commonly used in situations such as lotteries and games. Remember that you can always guess who would win the lottery. So as always, I'm going to show you manually how to how to compute some probabilities. Then in a different video, we're going to use Excel that I really like. Probably on request, we're gonna do some videos on how to use TI-84 or TI-89 or TI-83 to compute probabilities as well. Let's start with some basic concept of probabilities, as we said. The three comments, because we're gonna talk about we're gonna talk. Oh, sorry, not the three comments, because we said basic probabilities. Most of all, you know, probability plays a central role in the important statistical method of hypothesis tests. We're going to talk about it later. In probability, we deal with procedures such as generating male-female births or answering multiple choice questions that produce outcomes. So, to go there, we need to start with what we call events, right? So we need to define what an event is, okay? So an event is a subset of a sample space. So sample space is everything. This is where you need to list all the possible outcomes. But we said an event is a collection of results or outcomes of a procedure, right? So for example, if you roll a dice, how many possible outcome from a dice? The dice have six-sided, right? So you have six possible outcomes. If you flip a coin, how many possible outcomes? It's only two. You can obtain a head or you can obtain a tail. So roll a dice, for example, it's six-sided. Then possible outcome, you can obtain one, two, three, four, or five, or six. So we can consider an event as or flip a coin and obtain a number less than two. I mean less than three, sorry. two numbers that's less than 3 is 1 and 2. So 2 out of 6, for example, right? So that's an even. So a simple space, because as we said, we're going to go with each of them very separately, very quick. Talking about the simple space is an outcome or an event that cannot be further broken down into simpler components. So it's a very simple event. Like you flip a coin, you obtain a head. It's a very a simple event, right? Obtain a head is 1 out of 2 because you have two possible outcomes. You either obtain a head or a tail when you flip a coin. Then 1 out of 2 is a simple event. The sample space, as we said, is the place you put all the outcomes, right? So the set of all possible outcomes of a probability experiment is the sample space. Or if you see it here, we said the sample space for a procedure consists of all possible simple events. That is, the sample space consists of all possible outcomes that cannot be broken into further down. So very important you understand this. We are ready to talk about the common approaches three common approaches to find the probability of an event. So the three principle, when we do that, like notation for probabilities, we always use the capital letter P because what we need to do, remember, if we first list some basic notation, then we present the three common approaches to find the probability of an event. Remember, we talked about simple event, okay? And we talk about event and we talk about sample space, right? So, usually an event, let's say, okay, event, an experiment, right? You flip a coin. I mean, toss a die. Let's toss a die. Okay. Now, sample space, if you toss a die, right? What is the sample space? Let's call it S, right? The sample space, you can obtain 1, 2, 3, 4, 5, and 6. Or if I said a six-sided die, let me say a six-sided die because I want to make sure you don't take a different one. Now, even A, obtain a number less than 3, for example. So what are the elements of A? Because A is an event, so elements of A would be only 1 and 2. You can obtain a 1 and a 2. So you see, when we deal with events, we use capital letters like A, B, C, denote specific. So now to find probability of obtaining a number less than A is probability of A. That means, it's like the relative frequency. Take the number of the frequency of A, which is 1 and 2 elements, over the total, which is 6. So it should be 1/3. And all right, so doing 1/3, I believe that should be 0.33 repeated or 33%. You can either express it in terms of fractions or decimal, or you can do it as percentages like this one. So will you see here? P denote probability, A, B, C, D, or we can call it E also. These are all events. And P of something, P parentheses, the capital letter with a probability of A. So very important to see that. Now, the common approaches of finding, as we said, of finding the probability of an event, to find that probability, usually all probabilities, remember, it must be between 0 and, let's say, probability of A can be the smallest it can go is 0, the largest it can go is 1. Or if you want to write it in terms of percentages, probability is always between 0% and 100%, right? You cannot have more than that, okay? Now, when you deal with, if on a line of probabilities where you have 0%, 1%, 2%, right? You have 50%, right? And 99%, etc. And 100%. Remember, 100 is very certain this is gonna happen, right? But if you have 50% is like here, 50% chance. You said that there is 50% chance of obtaining something. Let's say when you flip a coin, there is 50% chance you obtain a head, or there is 50% chance you obtain a tail, right? But if you toss a die six-sided, right? What is the probability of obtaining a five? It's only one out of six. So if you do one out of six, you divide one divided by six, it would give you only 16.7%, right? Almost 17% of chance of obtaining a five out of a five when you toss a die. So your chance would be lower than 50%. So it's mostly unlikely when you do something, or it's more likely when it is above 50%, right? 0% is when it's very impossible. What is the probability of me traveling to a different planet this year? I would say it's 0% because I have nothing in plan for now for traveling to another planet. I'm certain it would be impossible to do it this year, right? But what is the probability, okay, of eating dinner tonight? So I'm certain it would be at least 75%. So I'm more likely this for this event to happen. When the following, as we said, three approaches for finding results in values are between 0 and 1. As we said, everything is between 0 and 1, or 0% to 100%. Always probability is never negative. Remember, probability should never ever negative. That's why the smallest is 0%, the largest is 100%, or you can say 1. And when you express it in decimal. So we said the relative frequency, relative frequency approximation of probability, conduct a procedure and count the number of times that event occur. Remember, when you toss a die, I did toss a die, a six-sided die. Sample space is 1, 2, 3, 4, 5, and 6. We said event A, for example, obtain a number divisible, I'm going to change it. Obtain a prime number. Obtain an even number. Yeah, I write number very badly. Okay. Obtain an even number. So what do you think A would be? Even A? So A would be, what are the even number from this sample space? Because you need to look at the sample space, not somewhere else. I mean, those are all the possible outcome when you toss a die. So even number is 2, 4, and 6. Now, what is the probability? How many data you see in this one? You see n is here 3, and n here is 6. Or we can say the frequency, how many times the number 0 by 2 okay, 3 times. So for us, this probability here, as you can see, we said the number of times A occurred 3 times over the total number of times the procedure was repeated, 6. So that would be 1/2 is 50%, 0.5, or it's 50%, right? Different ways of expressing the same thing. Now, we see again, classical approach to probability requires equally likely outcomes. If a procedure has n different sample events that are equally likely, and if event A can occur in S different ways, then probability of A equal number of ways A occurs over the number of different sample spaces. Again, it's S over N, or you can say frequency over the number of time over the sample size or the population size, etc. So that's very important to see that. We said also subjective to probabilities. The probability of event A as is estimated by using knowledge of the relevant circumstances. So we can use some subjectives, especially when trying to determine the probability that an individual car crashes in a year. We must examine past results to determine the number of cars in use in a year and the number of them that crash. Then we find the ratio of the number of cars that's crashed to the total number of cars, right? So that's very important. We look at the data, the statistics, the past reports to do that. We can do that also when you want to determine the probability of winning the grand prize in a lottery. We can do it by selecting six different numbers between 0 and 60. Each combination has an equal chance of occur, right? So there are very different ways we can see the subjective probabilities, right? Now, let's see some examples very quick. We're gonna just go very quick and look through some of them. Okay. If we go with esteem express the indicated degree of likelihood as probability between 50-50. Remember when it's for 50-50, it's right in the middle. For example, so if they ask you if you make a random guess for the answer to a true or false questions, that there is a 50-50% chance. All right, true or false? What do you have for true or false? Is it easy to find? Yes, true or false is a 50-50. One out of two. Or you can write it point 0.5 because it's true or false. Maybe it will be true or it's one out of two possibility for each of them. Based on a study of the movies made in a recent year, 33 out of every 100 movies have a female lead or co-leader. They said 33 out of 100. So they already tells you everything. All you need to do is either simplify it like this, or you can express it in decimal, or you can express it in percentages if you want to, if it asks you to do it in percentage. Based on the National Retail Federation survey, 47% of consumers turn down an online purchase if shipping is not free. Well, they already gave you the percentages here. There is nothing you can do. They said 47% means 47 over 100. That you can do 47, or you can express it in terms of fractions, or you can say it's decimal point 47. Three different or four different ways you can express it. When using a computer, when you use a computer to randomly generate the last digit of a phone number to be called for a survey, there is one chance in 10 that the last digit is zero. So when we talk about digit, remember digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is not a digit, it's a number. If you have two digits in a number, it's no longer a digit. So we have 10 digits, and they already tells you it's 1 out of 10. So you can just rewrite it 1 out of 10, or you said 1 divided by 10 is 0.1. Or you can say, it's 10%, right? 1 out of 10 or 0.1, or you can say it's 10%, right? So no problem for this. Those are some very easy examples we can cover. Here, talking about probabilities, as you know, probabilities are all about, fraction expressing fractions where you have the numerator as the frequency and the denominator as total number of total size or total population size. So let's say for an A, these are two exercises. In the first exercise, it states that Microsoft's Y-sort gender selection technique is designed to increase the likelihood that a baby will be a boy, right? At one point before clinical trials of the Y-sort gender selection technique were discontinued, 291 births consisted of 239 boys and 52 baby girls. Remember, when you have 291 babies, so 239 of them boys and only 52 girls, right? Based on data from a genetic and IVF institute, right? Based on this result, what is the probability of a boy born to a couple? Using that method. What probability you got a boy? Yes, you take the number of boy and you divide it by the total. That's it. Very simple. You can either express it like this, or if you do 239 divided by 291, it can also give you 0.821. Now, what they ask you next, does it appear that the technique is effective in increasing likelihood that a baby will be born? You say that, I mean, like 82% of the time, it's a boy. If it's 82% of the time it's a boy, yes, the technique appears to be effective, right? Yes, technique be effective. Yeah, because it's more than 50%. It's more likelihood to happen, right? Now, we go with another examples here where it says, in a circle survey of 3,000 adults, was found that 17% of the respondents do not carry any cash. Based on the result, what is the probability that a random selected adult carries no cash? They already give you that answer. You see, they already give you. It was for 17% of them. Now, if they want to know how many people would be different, you are going to take the 3,000, you multiply by 0.17. But here, they already give you the probability is 0.17, right? It's 0.17. You don't need to divide, do not do any multiplication in this case. They said, does it appear that most adults carry some cash? Yes, it's appear that most adults carry some cash. There are lots, right? 17% is very significant. It's a yes questions, right? As we move forward, you do not forget you can stop at any time to watch the videos again and see what we're doing. But we need to move to the next one because these questions on the on their first date, Kelly asked Mike to guess the date of her birth, not including the year. Okay, only like I mean, can not the year is not important, only the date. The date like or July 22nd or March 13 or April 9 or December 14 or May 22nd or October 2nd, etc. So those are types of numbers. So, but you don't need to put there. So what is the probability that Mike will guess correctly? Just guess. What is the probability? The first thing to remember is the number of days in a year. In a year, there are 365 days, right? 365 days in a year. Now, what day, how many days in a year that uh, Kelly might be born? You cannot have two different birthdays. You can have only one. So at this point, we're gonna say it's only one out of 365. Remember, we don't count the year, only the date. So that would be only one times in the entire year. So one out of 365. What would be unlikely for him to guess correctly on his first try? Okay. Would it be unlikely for him to guess correctly? Would it be unlikely? Yes, it will because it's very difficult. Yes, that's a big yes. It's very unlikely. B? Yes, very unlikely because what happened out of 365, it's a best chance. You would be very lucky, giantly lucky to say, oh, you were born on July 22nd. Out of 365 and to guess the exact date, this would be very unlikely. If you were Kelly and did guess correctly on his first try, would you believe his claim that he made a lucky choice, or would you be convinced that he already knew when you were born? Try in the first, correct guess in the first try? 365 and take exactly the exact date? No. Definitely already know. He already know. If he gets correctly on the first try, he already know. All right? Because in any way, it would be difficult. If Kelly asks Mike to guess her age, and my guess is too high by 15 years. 15 years, very high. What is the probability that Mike and Kelly will have a second date? Why, that would be no probability. That would be, is it 10%, 20%? 15 years. Like, instead of saying that Kelly was born in July 22nd, 1990, they said, oh, Kelly was born in July 22nd, 2005, like 15 years, or maybe 1975. See what happened 15 years ago? So there would be 0% chance for them if Kelly wants to base making the next decision about the next based on that guess, then there would be a 0% chance that ever happen. All right. Now let's see another examples because we pick up a few examples like this, 4, 5, 6, of course. In a recent year, in the United States, 83,600 passenger cars rolled over when they crash. 5,127,400 passenger cars did not roll over. 86 roll over. This number did not roll over when car crash. Find the probability of a random select passenger car crash result in rollover. What's the number for rollover? Probability would be the number rollover, which is 83,600 divided by what? Because in order to find probabilities, usually is over the total. So total for us, total of people in this study is 83,600 plus 5,127,400. When you add these two numbers, I believe it would probably, I don't know what it would give you. Let's see if I pick up a calculator, 83,600 plus 5,127,400. It gives us 5 million to 11 like this. So for us, it's 83,600 over 5 million to 1100. Now, doing this calculation, we can also simplify. If we simplify it, we're gonna have left maybe, simplest form, fraction in simple form, 418 over 26,055. Okay, now we can simplify into decimal, 418 divided by 26,055, answer would be 0.0160. Or if you express it in decimal, of course you can express it in decimal. If we try to express this in decimal, it's gonna just move the decimal point 2 digits to the right. When you multiply by 100, it's gonna give you 1.6%, right? So that's how we can express it if we want. Now the questions, is it unlikely? That means with a probability of less than 5%, because unlikely is less than 5%, like unusual event is less than 5% for a car to roll over in a car crash. Do we obtain less than 5%? Yes, probability is less than 5%. and 5%, right? As they said here, we said yes, yes. A passenger in a passenger car crash, a rollover is unlikely. I'm not gonna write everything, but we're gonna say yes, in a passenger car crash, a rollover is unlikely. I put two. Okay, right? So hopefully, for a car crash, for a car to roll over in a crash, right? So hope you got this one and you like it. Let's do one more in the sections. I mean, not the sections, this part, before we move forward. So this access. Each of two parent has a genotype, brown and blue, which consists of the alleles that determine eye color. And, and each parent contributes one of those alleles to a child. Assume that if the child has at least one brown allele, that color will dominate, and the eyes will be brown, right? The actual determination of eye color is more complicated than that, so we know that already. But what we're gonna do, first of all, the access to list. We can let's list the different possible outcome. We have two parents, right? Both either, I mean, the child may, both eyes may be brown, or brown blue, right? It may be brown or brown blue or blue brown. What else we can say? We have brown blue brown, or we can also have blue, right? It all depends of what the parent has. Now, those are the all possible different outcomes. We said these outcomes are equally to happen. Now, B, what is the probability that a child of these parents will have the blue type? Check blue type. How many you see here? You see one, two, three, four. That means N is four. How many blue you see? There is only one. So one out of four. That would be the answer. So the answer would be only one out of four. This is the only place you're going to have a blue. Now, what is the probability that the child will have brown? Check how many has brown. One, two, and three. So for C, it would be three out of the total, which is four. Very simple. We of course you're gonna use it to do more, but of course we need to talk about simulations in these sections. We're gonna try to go faster in it. Simulations, sometimes none of the preceding three approaches can be used. Remember, we talked about the three approaches that you can do, but maybe sometimes you cannot do none of them, like the relative frequency approximation probabilities, classical approach to probability, or subjective probabilities. We may not be able to do none of these. So a simulation of a procedure is a process that behaves in the same way as a procedure itself, so that similar results are produced. Probabilities can be sometimes be found by using simulation. Remember, we don't need to try to get someone fly an airplane from New York to Paris on the first day, right? They go to a school to become a pilot. So we need to make sure that they do some simulation. If we want to know the effect of alcohol on drivers, so we don't want any drivers to drink a ton of alcohols and drive. We need to do it using simulations. That's very important, right? Now, rounding probabilities, we said that when expressing the values of a probability, either give the exact fractions, or a decimal, or round up final decimal result to three decimal places. Like, if we said one half, when you divide 1 by 2, that gives you 0.05. So that's easy. But if you do 2/3, remember, if you divide 2 by 3, if you divide 2 by 3, what's gonna happen? It's 0.667. Now you should round up to 3 digits. You see, that's exactly what I do here, because when you express the value of a probability, either give the exact fraction or decimal, or round off final decimal with also three significant digits. In a different video, we did talk about significant digits already. Hopefully, you would have a chance to go back and review it, right? Because we're gonna need it for something different. Now, let's see in terms of large numbers, because that's something we're supposed to address also in this when finding probabilities with the relative frequency approach. We obtain an approximation instead of an exact value. As the total of observation increase, the corresponding approaches tend to get closer to actual probabilities. So this property is commonly referred to as the law of large numbers. So as a procedure is repeated again and again, the relative probability of an event tends to approach the actual values. We call it, as we said, uh, 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 the actual probability. That's very important. Now, laws of large numbers, then we have different ones. So, the laws of large number tell us that relative frequency approximations tend to get better with more observations. This law reflects a simple notation supported by common sense. So, a probability estimate based on only a few trials can be off by a substantial amount, but with a very large number of trials, the estimate tends to be more and more accurate. So the law of large numbers applies to behavior over a large number of trials, and it does not apply to any one individual outcome. If we know nothing about the likelihood of different possible outcomes, we should not assume that they are equally likely. The actual probability depends on factors such as the amount of preparation and the difficulty of the test. That's very important. Those are the questions we need to take in this case. Complements. Very important to look at another very important subjects in these sections is, sometimes we need to find a probability that an event A does not occur, and we call it the complement rules. So a complement of event A, we call it not A, A bar, if we call it A bar, so that means not A. All right. So that's very important to see it this way. So it says not A. So it's a not A, we call it that. You see that the event A is not happen, right? So for example, if you add all the probabilities together, probability that an event occur plus probability it doesn't occur must give you 100%. So anytime you know the probability of an event, so if I know the probability of A, it's easy to find the probability of not A. Just subtract it from the total, which is 100%. Very easy also to do at this point. Okay? Very, very easy to do it. So let's identify significant result with probability. Okay? When we do that, significant results with probabilities. What we mean by that, you know, um, the rare event rule for inferential statistics at this point, if under a given assumptions, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. So we can use you can use probabilities to identify values that are significantly, you know, that are significantly low or significantly high, right? Significantly high numbers of successes, we can use that. Um, like, let's say X successes among N trial is significantly high. Number of successes, if the probability of X or more successes is unlikely with a probability of 5%. If it's unlikely 5%, the probability, then X is significantly high number of success, right? So because that probability of X more is less than 5%. The values of 5% is not absolutely rigid, but we said also significantly low, X success among N trial is significantly low. Number of successes, if the probability of X or fewer success is unlikely with a probability of 5% or less. That is, if X is significantly low number of success, probability X or fewer, not more, or fewer, is less than 5%. So we're gonna do another few examples to cover it because that's very important to go over these few examples. The first one we're gonna cover because we're gonna talk about odds after. Use the given sample space or um, to construct the constructed required sample space to find the indicated probability. So that's what we're gonna do with this one. So let's try it. Very simple questions we ask in these. We said use the sample space listed in listing the 8 simple events that are possible when a couple has 3 children. Well, I list them here for you. You then have 3 boys, you have 2 boys, 1 girls, or we have 3 boys in a row, or you have 2 boys, 1 girls. Last, we have 1 boy, 1 girl, 1 boy, or you have 1 boy, 2 girls, or you have 1 girls, 2 boys, or you have 1 girls, 1 boy, 1 girls, or 2 girls, 1 boys, or 3 girls. So we have, if you have 3 kids, it's like a 2 power n, so 2 power 3 is 8 possible outcome. So maybe all 3 boys to one time, or all 3 girls one time, or you might have 1 boy then 2 girls, or 1 girl then 2 boys, or the girls will be in the middle, or the boys will be in the middle. So all depends. Now, assume that boys and girls are equally likely, so that the 8 simple events are equally likely. Find the probability that when a couple has 3 children, there is exactly 1 girl. So we know the total is 8 anyway, 8 possible outcome. But what is the probability you have exactly 1 girl? Look everywhere you see 1 girls in that sample space. Where do you see only 1 girls? I see 1 girls. 1, 2. I see 1 girls. 1, 3. That's it. So it's 3/8. So it's 2/8, or if you divide, that's 3.7375. Okay, that's it. That's a very simple examples. But we can do some exercises where we have more questions. For examples here, it says the county clerk in Essex, New Jersey, was supposed to use randomness to assign the let me try to put it smaller because I need some space for this. Instead of 20, how about 16? So we have enough space. Right. Okay, good. I'm hoping you still can read it. All right. So that's the one we're gonna do right now. We said the county clerk in Essex, New Jersey, was supposed to use randomness to assign the order in which candidates' names appear on voting ballots. Among 41 ballots, different ballots, Democratic candidate names were placed on the first line 40 times. The probability of a result that is high, remember when it's small, is oh my God, that's very small. It's like billions, kind of billions, right? Yes, that's it. You see, in order to get 1 point something, it's going to be very, very small. Assuming randomness was, that's exact, and that's really less than 5%, right? Assume randomness was used. Is the result of 40 Democrat candidate names being placed on the first line significantly low or significantly high or neither? When we look at this exercise, we said, I think we're going to go with the first one. It says that because the probability of a result such as 40 is small, right? They said the 40, yeah, 40 is small, right? I mean, that it's less than 5%. And because 40 is much higher than what is expected with randomness, if you try to do 40, it's going to be higher because they talk about it here. It's gonna be 40 when you do. Among the randomness was used is the result of 40 Democratic candidate names being placed on the first line, significantly low or significantly high, or neither. We would say that uh, the result of 40 is significantly high, right? Is result of 40 is significantly high. So we said it's really significantly high because the probability of a result such as 40 is small, and because 40 is much higher than what is expected with randomness. Okay. Now they said repeat part A after replacing 40 Democrats being placed on the first line of voting ballots with 26 Democrats being placed on the first ballots now. So instead of 40, we have 26. The probability of getting a result as high as 26 is 0.05. So it's it's pretty close in the middle, right? For this one, because the probability, I mean, what would we say? Is it significantly low or significantly high? Right? We believe the result of 26 Democratic mean placed on the first line is neither. Because look, 50% is like very close. It's neither. It's neither because the probability of a result as high as 26 is like 0.05863. So the result is not small. It's not less than 5%. You see, it's 0.058. So it's not less than 5%. It's neither. If you repeat the same exercise, replacing the 40 Democrats being placed on the first line of voting ballots with 14 Democrats being placed on the first line. Now you see we go down to 14. The probability of getting a result as high as 14 is 20, is 2 point something. You see 2.9, almost 3%. For this one, what would you say? The result of 14 Democrats being placed on the first line is significantly low. Why? Because significantly low for this one, because the probability of a result as low as 14 is 0.029792. That probability is small, right? It's less than and equal to 0.05, so it can be either high or low when it's less than this. But what happened is significantly low for these examples. Remember, we're doing as many as probabilities questions as possible. In this case, we're gonna have a chance to do more later, but for now, let's focus on what we have. The next examples we talked about. Let's say for the next examples, we said that in a SHRM, All right. In the XH, in the XHRM questions, okay. So what we're gonna do in this case, in a XHRM survey of 410 human resource workers, it was found that 148 of these workers have turned down job applicants because of information they found on social media. A job recruiter claims that less than 50% of human resource professionals have turned down job applicants because of information found on social media. If the true rate is 50%, there is a 0.0000978 probability of getting 148 of fewer human resources professionals who turn down jobs applicants because of information found on social media. If the true rate is 50%, is the result of 148 significantly low? So what does that suggest about the claim that the rate is less than 50%? So we're gonna try to do these examples now. So what happened, okay, remember we read it, we need to understand it because the questions is to answer if that probability of 0 point, a lot of 0 is low, right? Now, all you need to do is you need to decide, do you feel like this result of 148 is either significantly low or high or neither? I know the only I want to know is low, right? All right. When you look at this probability here of getting 148 or fewer human resources professional, you know it's less than 5%, of course, turn down. So we can say this is significantly low, okay, because of that probability is so low, right? So this one is significantly low, significantly low. All right. This suggests that the claim that the rate is less than 50% appears to be supported. So that's it. It's significantly low because of that probability. As you can see, it's very small. In a Pew Research Center of 1,060 teens aged 13 to 17, it was found that 604, or you can say 57% of those respondents have made new friends. You know, we have made new friend online. If the true rate is 50%, there is a probability of 0.0000306 of getting 604 or more respondents who have made new friends online. Is the 604 significantly low, significantly high, or neither? So what does the result suggest? Okay. So what does the result, what it suggest? Okay. So what we're gonna answer in this case, because because uh okay, let's see what happened. So, so because the probability, okay, because the probability of getting 604 or more respondents who have made new friends online is 0.0000306, that means less than 5%, it appears that 604 is significantly high. So we can say 604 is significantly high. Okay, so that's very important. It's really significantly high. This suggests that the true rate is not 50%. So true rate is not 50%. Okay, Very important to this one. Now, the last part of this section, so we're gonna probably review. So it's the probability review. We said the probability of an event is a fraction or decimal number between 0 and 1 inclusive. The probability of an impossible event is 0. The probability of an event that is certain to happen is 1 or 100%. We said probability of A, the probability that the event occur. Probability of not A, where you put the bar, is the probability that the event does not occur. So we put a bar on it, or it's in some books, they're gonna put it like this, not A, or they can even do it just probability not A. So different ways of writing the same thing, not A. I mean, they are all the same, so it's all depend which books you use. Okay, so very important. Odds, something we need to review. Also, the second part of it, expressions of likelihood are often given as odds, such as like 50 to 1. Here are, very important. So the actual odds against A, even A, okay, are the ratio. So we usually use ratio for that. Very important to use ratio. Odds make it easier to deal, for with these types. So we said it really makes it easier to deal with money transfer associated with gambling. That is why odds are commonly used in casinos, lotteries, and racetracks. Probability makes calculation is years when you use odds, all right? We see that these definitions, like the actual odds against event A occurring, the ratio not A, probability of not A over probability of A, usually expressed in the form of ratio A colon B or A to B, where A and B are integers, reduced using the largest common factor. If A is 16, B is 4, express the odds as 4 to 1 instead of doing 16 to 4, right? Very important. And also the other odds, because we have three definitions for it, the actual odds in favor of, against, in favor of event A occurring, the ratio. Now, the probability that the event A occur over the probability of event A not occur, which is the reciprocal of the actual odds against that event. If the odds against an event are A to B, then the odds in favor is B to A. So very simple, so we can do that. And the other definitions is the payoff odds against event A occurring, the ratio of net profit if you win to the amount bet. Okay, very important again. We can do that. So we said payoff odds against event A equal net profit colon amount odds. So these definitions reflect the actual likelihood of an event. Of an event, but the payoff odds describe the payoff amounts that are determined by casino, lottery, racetrack operators. Okay, so racetrack and casinos are in business to make a profit. So the payoff odds will not be the same as the actual odds, right? Because they want to make money. But let's see in a few examples what we can do. Here, a wallet wheel has 38. We said a wallet wheel has 38 slots. One slot is 0, another slot is 0, 0, and the others are numbered from 1 through 36, respectively. You place a bet that the outcome is an odd number. So if you take 36, 1 to 36, how many odd numbers do you have? Remember odd, an even number, odd, even number, odd, even number? Remember that? Well, if you take odd numbers like 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. So the number of odd numbers in this case would definitely be odd, would be 18, right? Because 36, half of it would be odd. So what is the probability of your winning if you place a bet on the odds? That would be 18 over 38 slot available, right? So if you do that, or you can express it in decimal, this is 0.474 when you use a calculator. What is the extra odds against winning here? You know, if you try to do it, um, actual odds against winning, it's you know, you can simplify it definitely it's gonna be um, a 10 to 9. Okay, so because remember, if you look at, let me erase it. Probability 10, 9. So how do I find it? Remember, probability you win is because you said find the probability you win over probability you don't win. So odds against probability you don't win. Okay. So if you take the probability you don't win, okay, look at that. If you take the probability, because now you know the probability you win, what is the probability you don't win? Probability you don't win would be what? 20? Like for us, probability of A is 18 over 38. Probability of not A would be whatever you have left from 100. So that would be 20 over 38. So look, if you take probability you win, you don't win, over probability you win, look, go back there, you will see it. Okay. This is what's gonna happen. You have 20 over 38, 18 over 38. So what happened? You fraction on the top, multiply by the reciprocal of the second fraction. You cancel the 18. You have 20 over 18. Simplify by 2, both sides. So if you divide both numerator and denominator by 2, it gives you 10 over 9. So we can write our against winning, as we said, like you have 10 over 9, or you can write it in terms of ratio like this, 10, 9. Okay, so when you bet that the outcome is an odd number, the pairs of odds are 1, 1, right? Because how much profit do you make if you best if you bet 18, right? When you bet, if you bet, not best, sorry, I need to clean this up. $18 and win. If you win $18, well, it's 1, 1. If it's 1, 1, then how much you gonna win? Only $18. It's a 1, 1. You either win $18. And next is would say, how much profit would you make on the $18 bet if you could convince the casino to change its payoff so that they are the same as the actual odds against winning, like recommendations, we said don't actually try to convince any casino. So look, the best you can do is $20. Remember, we said you either win $20, $18, or you lose $20. So the best you can do is really win $20. I'll leave the last examples for you because it's already close to an hour we've been in this video. In a different video, we're going to come back with section 4.2, addition rule and multiplication rule. Don't forget to look for my Excel videos, like where we explain how to use Excel to perform some probabilities. Take care.